Before plunging into the nuances of the declaration, it is vital to first fathom the size of what is being referred to. The Large Hadron Collider, LHC, operated by CERN, represents an exceptional accomplishment in the domain of scientific advancement. Spanning a vast 17 miles, this cutting-edge network of superconducting magnets stands as the most powerful particle accelerator ever constructed. It serves not only as a remarkable display of human creativity, but also as a symbol of the astonishing progress we've made in understanding science. The LHC has the remarkable ability to recreate the conditions that were present at the birth of the universe. However, as we embark on exploring the vast mysteries of the cosmos, a crucial question arises. Could this state-of-the-art machine, designed to uncover the deepest secrets of the universe, also pose unforeseen risks? CERN, founded in 1954, is one of the most prestigious scientific organizations in the world. With 23 member nations and an extensive research community, it serves as a hub for collaborative research and groundbreaking discoveries. While the LHC is undoubtedly its flagship project, it is only one part of a much larger network of particle accelerators and experiments. Rather than imagining it as a racetrack for cars or animals, consider it a high-stakes race for subatomic particles. These particles participate in a race that tests the limits of speed, precision, and even the very nature of reality itself. Inside the LHC, protons are accelerated to nearly the speed of light, replicating the energy levels present at the moment of the Big Bang. The resulting collisions generate temperatures far greater than those at the Sun's core. A series of magnets guide the protons along their designated paths, while advanced cooling systems ensure that the magnets remain at temperatures colder than space. These collisions are carefully orchestrated at 4 specific locations within the accelerator, where specialized detectors, ATLAS, CMS, ALICE, and LHCb, capture data. Each of these detectors serves a unique function, offering different perspectives on the aftermath of these ultra-high-energy impacts. Together, they act as colossal cameras, recording the results of these collisions, while scientists meticulously analyze the remnants to identify elusive particles like the Higgs boson, often referred to as the God particle, as well as other phenomena that could shed light on the fundamental components of the universe. By focusing on subatomic particles, researchers aim to gain a deeper understanding of the fundamental structure of our universe. Yet, with every new discovery at the LHC, even more questions arise. The ethical and existential dilemmas. The LHC is not just a machine, it is an embodiment of humanity's relentless curiosity and unwavering pursuit of knowledge. It represents our desire to comprehend the forces that shape our very existence. But as we push the boundaries of the unknown, we must confront the ethical and existential dilemmas that accompany this exploration. What dangers could arise from probing the unknown? Could our insatiable quest for knowledge open doors to forces beyond our control? At CERN, where the limits of human understanding are being tested to their fullest, a disturbing realization has surfaced, one that has unsettled even the most seasoned scientists. Brian Cox, a former CERN researcher and a highly respected figure in particle physics, recently made a statement that has both fascinated and alarmed people worldwide. Cox revealed that the LHC is designed to simulate a miniature version of the Big Bang, essentially, a small-scale explosion of the universe's birth. He elaborated on the LHC's immense potential to make groundbreaking discoveries, such as unveiling the secrets of dark matter, a mysterious substance that comprises a significant portion of the universe. Harnessing the fundamental forces of the universe is undoubtedly exhilarating, but it also carries profound risks. This miniature Big Bang is not a mere theoretical concept, it is a real phenomenon occurring within the LHC. The collider recreates extreme conditions of heat, pressure, and energy, mirroring those present at the dawn of the universe. Perhaps we are witnessing the birth of time itself. However, with such immense power comes a tremendous responsibility. What if something goes wrong? Historical precedents. The case of Anatoly Bugorsky. This concern is not new. In 1978, Russian physicist Anatoly Bugorsky experienced an event that changed his life forever. While working with the U-70 synchrotron at the Institute for High Energy Physics in Protvino, Russia, a malfunction caused a proton beam to accidentally cross his path. Traveling at unimaginable speeds, the beam entered his skull, piercing through the back of his head and exiting through his nose. Despite witnessing a flash of light brighter than 1,000 suns, Bugorsky remained conscious and walked to seek medical attention. The outcome was both shocking and terrifying. He lost hearing in one ear and suffered partial facial paralysis. Yet, Despite the severity of his injury, his cognitive abilities remained intact, and he continued his scientific work. Bugorsky's experience serves as a grim reminder of the immense power and potential risks associated with particle accelerators. Could the LHC create a black hole? The dangers of machines like the LHC should never be underestimated. Some scientists have voiced concerns about the possibility of unexpected reactions that could alter the very fabric of reality. For example, there are fears that the LHC could potentially create a microscopic black hole. Black holes are regions of space where gravity is so intense that not even light can escape. These cosmic phenomena exist at the edges of the universe, and the idea that the LHC could create even a tiny black hole is both thrilling and terrifying. Could such a black hole grow uncontrollably, eventually consuming the Earth from within? Scientists at CERN have attempted to reassure the public, stating that any black hole created within the collider would be highly unstable and would evaporate instantly. Still, the remote possibility of such an event has sparked widespread debate and concern. To understand how the LHC could create a black hole, one must first grasp the fundamental mechanics of a particle accelerator. When protons collide at near-light speeds, the energy released is so immense that it can warp the very fabric of reality itself. Imagine a trampoline stretched tightly. If a heavy object is dropped onto it, the fabric bends. If the object is massive enough, it can create a deep depression, pulling everything nearby into it. This analogy illustrates how the LHC could affect spacetime at the quantum level, where the laws of physics become unpredictable. One theory suggests that extra dimensions beyond the familiar three of space and one of time could exist. If such extra dimensions do exist, the LHC might be able to access them, potentially creating a gravitational well that could lead to a tiny black hole. This idea has attracted the attention of renowned physicists, including the late Stephen Hawking. In his writings, as physicists, we've enthusiastically guessed this moment for more than a century. Beginning around 1916, this occasion marks a momentous accomplishment, offering a brief glimpse into one of the universe's most fascinating and confounding phenomena, black holes. These cosmic monsters, known for their immense gravitational influence, remain incredibly elusive. While they are epic in terms of their gravitational impact, they are nearly undetectable to us, making them even more mysterious. One such black hole, possibly weighing between 2 to 4 million times the mass of our Sun, may be the subject of this discovery. Over the past several decades, research dedicated to black holes has transformed our understanding, taking us from a state of absolute ignorance to one where we are beginning to get an intimate look at them. And now, things have taken an even more thrilling turn. Physicist Michio Kaku has revealed that we have finally figured out how to look inside a black hole. This discovery opens the door to an abundance of new information that could illuminate aspects of science we may have previously overlooked. Let's take a deep dive into the realm of black holes and uncover what exists within them. Understanding black holes. While space is vast and infinite, the concept of black holes raises endless questions. Before we delve into the specifics of Kaku's groundbreaking findings, it's essential to understand the fundamental nature of black holes. Most people have at least a basic understanding of what black holes are, but significant gaps in our knowledge remain. The theory of black holes dates back to 1916, when Albert Einstein published his general theory of relativity. This theory predicted the existence of black holes, though at the time, the idea was purely theoretical. It wasn't until around 50 years later, in the 1960s, that concrete evidence for their existence began to emerge. Scientists studying the Cygnus constellation observed an unusually bright blue star emitting X-rays. They discovered that this star was not stationary but rather orbiting a massive dark object. Upon further investigation, it became clear that these X-rays were being pulled into this object, leading to the coining of the term black hole. This discovery was a significant turning point because it confirmed that black holes were not merely the product of Einstein's imagination, they were real, tangible entities that existed in space. It became evident that scientists needed to study them more thoroughly. The study of Cygnus X1. Researchers worldwide began focusing their studies on a particular black hole in the Cygnus constellation, designated Cygnus X1, located approximately 6,000 light-years from Earth. This black hole was more than 10 times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that not even light could escape. This was the defining characteristic of a black hole, the ability to trap light within its gravitational grip. The nature of a black hole is both fascinating and terrifying. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape its pull. Any object that ventures too close is sucked in, and once it crosses a critical boundary, it is lost forever. This inherent danger is why expanding our understanding of black holes is so crucial. The search for more black holes. After the discovery of Cygnus X1, scientists launched an extensive search for other black holes. Estimates now suggest that there may be more than 100 million black holes scattered throughout the Milky Way galaxy. However, due to their nature, these enormous giants are incredibly difficult to detect, meaning we don't have an exact count. What is clear, though, is that there could be millions of black holes within our galaxy, highlighting their importance in cosmic research. The primary concern surrounding black holes revolves around their immense gravitational force. Their gravity is so powerful that anything that gets too close is gradually compressed to an extreme degree until it becomes a singularity. Simply put, black holes function like cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most unsettling aspects of black hole research is what happens to an object, or even a person, falling into one. Due to extreme tidal forces acting upon them, they would be stretched into a long, thin shape in a process known as spaghettification. This stretching would occur gradually, and the individual would perish long before reaching the final stage of the process. So, to be clear, it's best to avoid falling into a black hole at all costs. Capturing the first image of a black hole. In 2021, a remarkable milestone was achieved when scientists successfully captured the first clear image of a black hole. This particular black hole was located in the M87 galaxy. The research team took multiple images over several nights and stitched them together to create a comprehensive photograph that revealed astonishing details. It turns out that a black hole is not just a giant void of nothingness, as many might assume. The structure of a black hole. A black hole consists of three distinct layers. 1. The event horizon, the outermost boundary. Once an object crosses this threshold, there is no turning back. It will inevitably be drawn into the black hole. 2. The photon sphere, a region where light itself can be trapped in orbit around the black hole. Any light entering this zone becomes ensnared by the black hole's gravitational pull, unable to escape. 3. The singularity, the innermost point, where all matter that falls into the black hole is crushed down to an infinitely small space. Here, the laws of physics as we know them break down entirely. What's even more fascinating and alarming is that no two black holes are exactly alike. While they all adhere to this three-layer structure, their behavior can vary dramatically from one to another. Observing black holes. Typically, scientists rely on telescopes to observe celestial objects. However, when it comes to black holes, this method At the same time, these findings highlight the necessity of collaboration between scientists from different fields. Cosmologists, astrophysicists, and researchers from diverse disciplines must work together to interpret the data provided by the JWST and ensure that these discoveries are integrated into our broader understanding of the universe. The complexity of the universe demands a multidisciplinary approach, and the JWST discoveries are a perfect example of how scientific collaboration can lead to major breakthroughs in our understanding of the cosmos. As scientists continue to analyze data from the JWST, they are also refining the tools and techniques used to measure and interpret cosmic phenomena. The precision required to study galaxies that formed billions of years ago is immense, and each new discovery forces researchers to improve their methods and update their models. This constant process of refinement ensures that science remains a rigorous and self-correcting field, where new discoveries lead to the betterment of our overall understanding. As we continue to explore the universe, the discovery of these massive galaxies will undoubtedly prompt new questions and hypotheses that will guide future research. Will the discovery of these universe breakers alter the way we think about the formation of galaxies or even the very structure of the universe itself? Only time will tell. However, one thing is certain. The revelations of the JWST have reignited our curiosity and opened new frontiers in the study of the cosmos.